Okay, it's a pleasure to introduce Honghao Fu to give the last talk of the session on the membership problem for constant size quantum correlations is undecidable. And just a reminder that your screen is not full screen right now.
Oh yeah, thanks. Okay. Yeah, so hi everyone. Today I'm very excited to present my joint work with Carl Miller and William Slofstra. We prove that the membership problem for constant size quantum correlations is undecidable. This talk will have 3 parts. In the first part, I will go over the basics of quantum correlations. In the second part, I will formally introduce the membership problems and state our main results. In the last part, I will demonstrate the main ideas of the proof. So the study of quantum correlations goes back to the 1960s when John Bell first observed that local measurements on entangled system can give rise to correlations that cannot be simulated classically. Now this scenario is referred to as a Bell test. In a typical Bell test, there are 2 parties, Alice and Bob, who cannot communicate, but they may share entanglement. Each of them is going to be asked a question and they need to provide an answer. Alice's question is denoted by X and her answer is denoted by A. Bob's question is denoted by Y and his answer is denoted by B. Note that if we add some distribution of the questions and some rules to determine if the answers are correct or not, then a Bell test becomes a non-local game. We're interested in the behavior of Alice and Bob, which is described by a collection of conditional probabilities of their answers given the questions, which is also known as a correlation. So we can view a correlation in a correlation matrix, where the columns and rows are labeled by Alice and Bob's question-answer pairs. In the simplest case, when Alice and Bob's question and answer sets are binary, a correlation is given in this table. To read this table, for example, if Alice's question-answer pair is 1, 0, and Bob's question-answer pair is 0, 1, then in this intersection, you have a probability for Alice and Bob to answer 0, 1 for the question 1, 0. So you can see that in general, the size of a correlation is a product of the sizes of the question and answer size. Next, let me make some comparison between classical and quantum correlations. We know classical correlations can be generated by local measurements on local systems with shared randomness. The set of all the classical correlations is denoted by C sub C, which is a convex polytope. For quantum correlations, we know they can be generated by local measurements on some quantum system. And in fact, quantum correlations can arise in 4 different models. Let's fix the number of questions and the number of answers to be NA-NB and MA-MB. We first define the set C sub Q of NA-NB, MA-MB to be the set of all the quantum correlations that can be generated by local measurements on a finite dimensional quantum state. If we drop the requirement about the finiteness and allow measurements on infinite dimensional quantum states, then we are in the set C sub QS of NA-NB, MA-MB, where S stands for spatial. And lastly, we define CQA to be the closure of the corresponding CQ set. Here, A stands for approximate, and this set contains all the correlations that can be approximated arbitrarily well by correlation from the CQ set. And lastly, we drop the requirement about the tensor product structure and simply require Alice and Bob's measurement to always commute. Then we are in the commuting operator model, and the corresponding set is denoted by C sub QC. For the 4 models, we define the overall set C sub T to be the union over all the different sizes. And for the 4 sets, we know they are all convex, and by definition, CQA is closed. We also know that CQC is also closed. So this makes us wonder if the 4 models are equivalent. Actually, now we know they are not. The separation between CQS and CQ is first proved by Claude and Stark. The separation between CQA and CQS is first proved by Slofstra. And the last separation is given in the MIP star equal RE paper by Ji, Nataraj, and Vedic, Wright, and Yuan. Knowing the 4 models are not equivalent is an important step. About the individual size, we know in the 2222 case, the 4 models are equivalent. And we can focus on qubit strategies. And we also know how to describe the synchronous subset of the set C sub Q3322, which is proved by Russell last year. But beyond this point, very little is known. So we wonder if we can get descriptions of the sets of quantum correlations. Here by description, we mean some analytical expression that can be checked by a computer in a finite amount of time. This question is important for two reasons. The first one is that such descriptions can tell us what we can do with entanglement. So it will give us more insights into what we can achieve in quantum experiments. The second reason is that it will improve our conceptual understandings of entanglement. And we decided to study this problem from the computational complexity perspective. Namely, we would like to study the membership sub T problem for T in the set Q, QS, QA, and QC. In this problem, you are given four numbers, A, NB, MA, and B, which will specify the size of a correlation and a correlation of this particular size. Your task is to determine if this correlation P is in the set C sub T or not. Here, we focus on correlations that has entry that can be expressed in a finite amount of space. So we don't work with correlations with non-algebraic entries. The reason to study this problem is the following. So if finite length description of the set C sub T exists, then we can use it to determine the membership of any correlation P. Then this problem would be decidable. However, now we know this problem is actually undecidable for all the four models of quantum correlations. They study a related problem, which is to determine if the maximal quantum winning probability of a nanohoop game is 1 or below 1. And this results imply that there exists some families of correlations such that determining the membership of the correlation in this family is equivalent to deciding if a Turing machine holds or not. And so more formally, they mean that you cannot find a uniform description that will work for all the correlations of different sizes. But what about correlations of fixed size? This result doesn't rule out the possibility for a finite length description for the set of correlations of the same size. Therefore, we study this more restricted version of the membership problem, which is called the membership of NA, NB, MA, MB sub T problem. So you can see the size of the correlation is encoded in the problem itself. And this problem asks, given a correlation of this particular size, is this correlation in the set C sub T or not? So the difference between this one and the previous one is that now you are promised to always get a correlation of this particular size. So your algorithm doesn't need to work for correlations of different sizes. So in principle, this problem is easier than the previous one. And we would like to know if this problem is decidable for all the different sizes. And in our main result, we find out that there exists a constant NQA such that for NA, NB, MA, MB greater than capital NQA, the membership problem for fixed size CQA correlations is undecidable. And similarly, there exists a constant capital N sub QC such that for NA, NB, MA, MB greater than NQC, the membership problem for fixed size CQC correlation is also undecidable. Intuitively, it means that on the boundary of some quantum set of correlations, there is a boundary correlation such that the problem of determining the membership of correlations around this boundary correlation is impossible, no matter how close the correlation is to this boundary correlation. And more formally, it means that if the size of the correlation is large enough, then you cannot write down a finite length description of the set of correlations of this particular size. So it means that the hardness of the general membership problem is independent of the size of the correlation. To prove these results, we use embedding procedures developed by Slofstra and some self-testing techniques from my previous work. For today, we will focus on the CQC case to demonstrate the main ideas. So before I go into the proof itself, let me first introduce group presentation. Let S be a set of symbols and Fs be the free group generated by S. And let R be a subset of Fs. So if a group G is defined to be the quotient of Fs modulo the normal subgroup generated by R inside Fs, then we say the presentation of the group G is S:R, where S is a set of generators and R is a set of relations. So if both S and R are finite, then we say the group G is finitely presented. So you can think about the group G as a set of words spelled by letters from the set S and then simplified by applying the relations from the set R. Next, I will give two examples. The first one is the dihedral group. In this group, there are two generators, T1 and T2. And the relation says that the order of T1 and the order of T2 are 2, but the order of the product of T1 and T2 is P. So this group is finitely presented, and it is also a finite group. In the second example, I will give the presentation of the solution group associated with a linear system AX = 0. This is a binary linear system, and it has m equations and n variables. In the presentation of the solution group, there are n generators, one for each variable. And the relation says that the order of each generator is 2. And if two generators are coming from the same equation, then the two generators commute. And lastly, if you take the product of all the generators from the same equation, you should always get identity. The motivation behind introducing this group is because a representation of this group can give us a perfect strategy of a linear system game. So a linear system game is one of the non-local games where Alice is asked to give an assignment of an equation and Bob is asked to give an assignment for a variable from Alice's equation. They win this game if Alice's assignment is satisfying and they are consistent with the assignment to the common variable. Next, I will introduce the embedding procedure. So first of all, an embedding is an injective homomorphism from the group G to a larger group K. And Slofstra proves that we can embed any finitely presented groups into solution groups. And in this procedure, he gave us the formulation of the solution group and the formulation of the injective homomorphism. And you can see that this embedding procedure is widely applicable. So he introduced this embedding procedure to study quantum correlations in the following way. So let's suppose you embed the group G into a solution group gamma. Then he proved that there exists a correlation P to check if the generator Xi is non-trivial in the solution group gamma. More specifically, this correlation P is in CQC if and only if Xi is non-trivial in gamma. So if gamma is non-trivial, you can use the regular representation of the solution group to get an inducing strategy of the correlation P. If it's trivial, then you can prove that no commuting operator strategy can give you this correlation P. And this is developed by Kudron and Slofstra. One thing to note is that the size of the correlation P depends on the presentation of the solution group gamma. More specifically, it depends on the number of generators and the number of relations. In our case, we are going to apply this embedding procedure to a group that can simulate a Minsky machine. The most important property of a Minsky machine is that it can simulate any Turing machine with a polynomial overhead. And it has a very simple structure as it only has k different counters, which can be thought of as glasses that can hold arbitrary amount of coins. Now for each counter, there are two types of operations. The first one is to increment the counter, just like you add some coins to some of the glasses. And the second type is to decrement the counter, which is like removing coins from some non-empty glasses. You can see that the commands of the Minsky machine are very easy to describe. So we can simulate a Minsky machine in a group developed by Harlan-Povich, Myasnikov, and Sapir. In this group, there's a group element or word W of C for each configuration of the Minsky machine. This configuration basically tells us which state the machine is in and how many coins are in each of the glasses. And two words W of C and W of C prime are equivalent in this group if and only if there's some computation of the machine that will bring one configuration to the other. This is why we say this group can simulate a Minsky machine. So among all such words, we are interested in the words W of N and the word W of A. W of N is for the starting configuration of the Minsky machine with input N, and the W of A is for the final accept configuration. You can say that W of N equals W of A if and only if the input N is accepted by the Minsky machine. Then Kuzhong and Slofstra did it first, so they embed the group GMM2 into a solution group and construct a correlation P sub N, which will check if W of N is not equal to W of A in the simulation group. If you consider all the different N's, you can get a family of undecidable correlations, and then they prove the membership problem for CQC is undecidable. But one thing to note is that the size of Pn here is exponential, and we need some extra techniques to drive the size of the correlation from exponential to constant. So we need some techniques from the self-testing result. I prove that for any prime P with primitive root R, there exists some correlation P sub PR whose size only depends on R, but it can self-test a P-1 dimensional maximum entangled states. Here, by being a primitive, I mean R is a generator of the set of the multiplicative group of integer modulo P. Intuitively, you can think about it as the prime P is written into the entries of the correlation instead of the size of the correlation. And one important observation that we make is that if a strategy with a shared state set can induce the correlation P sub PR, then Alice and Bob must have binary observables T1, T2 such that the product of T1, T2 raised to power P acts as identity on the shared state side. If you can recall the three relations of the dihedral group, this correlation effectively certifies all of them. In our case, we need to modify this correlation a little bit so that it can be induced by the regular representation of the dihedral group. But at the same time, the size of the correlation still only depends on R, and it can still certify all the three relations from the dihedral group. But one thing to note is that the modified correlation is no longer a self-testing correlation. So in our proof, we first construct a set Q, which has element of the form P of N. And here, P of N is nth prime with primitive root R from set 2, 3, and 5. And X is a recursively enumerable set. So you can think about the set X as a set of all the halting instances. And here we choose R from this side to make sure there are infinite many such primes. And you can convince yourself this set Q is also recursively enumerable because checking if input is a prime with a fixed primitive root can be done in only a finite amount of time. So we can let MM3 to be a Minsky machine that can enumerate the set Q, meaning that MM3 accepts an input if and only if the input is from the set Q. Then we can look at the simulation group GMM3, and we make an extension to add an element T to this group such that if you conjugate the word W0 by T n times, you will get the fixed word W of N for all the possible N. This means that if you set the order of T to be N inside this extension group, we will have Wn equals W0. Then we can look at the quotient group, where we take the extension group and modulo the relation T to the Pn equals identity. So this is how we set the order of T inside the extension group. In this group, while the properties are introduced above, we can say that W0 equals W of A if and only if P of N is accepted by the Minsky machine MM3. Then we can apply the embedding procedure and the self-testing correlation to get a correlation P sub N such that P sub n is in CQC of NQC, NQC 8 and 8, if and only if W0 is not equal to W of A inside the quotient group. So here, the reason that the constant NQC is independent of small n is because roughly the correlation has two parts. The first part checks if the correlation satisfies all the relations from the extension group. Since the presentation of this group is fixed, the size of the first part is fixed. The second part checks this relation, and P of n changes, but the size of this part only depends on the primitive root R, which is also fixed. So the size of the correlation is fixed. And this is how we prove the undecidability results of the CQC case. And for the CQA case, we take a similar approach. The only difference is that we need to prove more properties of the extension group, and we need to apply a different embedding procedure to this quotient group. So in summary, we have proved that for the CQA case, the membership problem for fixed size CQA correlation is core-RE hard. But this bound is not tight because Musavi, Najadi, and Yuan proved last year that the upper bound for this problem is one level up in the arithmetical hierarchy. And we leave the text to close this gap for future work. But for the CQC case, we prove it's core-RE hard, but this problem is actually inside core-RE, as shown by Navascu's, Pironian, and Asen in the NPA hierarchy. So now we know this membership problem for fixed size CQC correlation is core-RE complete. And this is the end of my talk. Thank you very much for listening.
Thank you very much. Big round of virtual applause.
Thank you.
There is one question from Gemma de las Cuevas about the encoding of the input. So how are these reals represented? It seems like they would not have a finite description in themselves.
Yes, we don't consider all the real numbers. We consider like some subfield of the real numbers, which has like algebraic numbers, so they can be expressed as a root of some integer value polynomials. And we only consider those kind of entries.
Okay, thanks. There's a question from Henry Yuen, who also happens to be on the call right now. So Henry, do you want to take turn on your microphone?
Hey, Honghao. Can you give a guess for, or do you know what this number NQC or NQA might be?
No, we didn't estimate. Like, so the NQC actually depends on the description of the rules of this group MM3, and we didn't estimate like how many comments are in this MM3, and yeah, that's the only missing part. We know how many generators we need, but we don't know how many relations we need for this group.
Do you have a sense whether it's closer to like 400 or 2 to the 400?
I think it's larger than 400.
Okay.
But I'm not sure it's close to 2 to the 400. Yeah, thanks.
Thanks.
Okay, thanks a lot. A question from Itai Lee. If we allow for a fuzzy unknown area around the boundary, so a promise problem that we don't get instances from there. So I guess a promise that we don't get instances from some sort of fuzzy boundary. Can we decide whether correlations outside this area are inside or outside of C underscore QA or C underscore QC?
Yeah, I think the question is about the approximate version of the membership problems. Here we studied the exact case. And I think for the, let me go to the slide. I think from the MIP star equal RE paper, we know that the approximate membership problem for CQA, CQS, and CQ are undecidable. And I guess it's RE complete, something like that. But we don't know what it's like for the CQC case in the approximate case. Yeah, that's my answer.
Okay. We still have a couple of minutes, so we can hold on in case there are more questions coming into the Slack, or Henry, if you have any questions, feel free.
Actually, one question I have is about, you talked about this boundary thing and I didn't fully understand. You said that you had a stronger result where you said even.
Yeah.
Yeah, can you elaborate more on that?
Yes, so we are thinking about looking at the limit of all the correlations in our undecidable family of correlations. I think we think there's a fixed limit point of that correlation, of this family of correlations. And if you look at the limit point and consider all the correlations around this limit point, then I think it's impossible to decide correlations around this limit point, because if you can decide that, then you can decide the membership for our undecidable correlations. And that's the logic we have.
And by around, do you mean with some fixed distance, or?
Yeah, I think we mean for any positive distance from this like limit point, and no matter how close or how small the distance is, you cannot decide the membership.
I see. So even this specific point in the correlation set somehow captures the hardest part of determining membership in this whole set.
Yeah, yeah.
I see. Very cool.
Thanks.
Thanks.
Question from Cedric Lin. As a follow-up to what Henry had brought up, do you have an algorithm? Sorry to bother you with this one. Do you have an algorithm to give any upper bound about NA? We really want to know about the NA.
Sorry, NA, what do you mean by NA?
Oh, it's the same NA that Henry was asking about. Okay, and once more, do you have an algorithm to give any upper bound for NA?
Oh, I think it's NQA. Sorry, I missed the Q. Yeah, the size.
I see. I think you can. I think there are some. I think there should be some way to derive the upper bound for the size. So the size of this NQA depends on like the size of the Minsky machine or the Turing machine for the halting problem. I think there should be some way to derive an upper bound on the size of that Turing machine, and then we can turn that upper bound into an upper bound of the constant n sub QA. That's yeah, but I don't have a concrete way to calculate it, but I think there should be a way to calculate it.
Okay, thanks. And a question from Matthias Caro. Can you comment on how exactly your result is related to MIP star equals RE? Are the two results comparable in the sense that one implies the other, or are they incomparable?
I guess I think it's hard to compare. First of all, our approach is like purely from computability, and that result is from complexity, computational complexity. It's like two different approach, and our result doesn't imply any separation between CQA and CQC, but their results implies a stronger result. And the other way to think about this is that our case, we have like fixed number of questions and fixed number of answers, but for their results, they have increase in size of the neighborhood game. So it's hard to compare, yeah.
Okay, thank you very much. I'd like to remind the attendees and the speakers that they can now head over to the roundtable discussions. The link is under the stage, and these are Zoom sessions where you can have discussions. And with that, I'd like to thank all the speakers for this session.
Thank you.